Okay, wonderful. All right, so yes, this talk is a bit outside probably your normal research, also actually outside my normal research. This is about astronomy and the climate crisis. And as Volker already said, this has come up relatively recently, although the climate crisis has been around the knowledge for decades actually, but it's really only in the last few years that it has increased in attention, and that also from myself, for example, I only realized really how urgent and how dramatic this is 2 or 3 years ago, and then started to talk and discuss more about this and also collaborate with other people to try to solve it. So I'm going to talk, I have a fairly big introduction about the sun, planetary orbits, ice ages, and what is the climate crisis. To put these things in context, this is partly because I hope it's interesting for everyone, and also I think it's not perhaps knowledge or information that is too much around. So perhaps that helps to put this on a footing. And then, of course, I'm going to discuss astronomy's carbon footprint, which is, of course, the core topic of this talk. So what are our emissions? Where do they mostly come from? And how can we reduce them? But then also the other part of what astronomy can do, namely to convey this message of there is no planet B. This is, in my view, actually the more important part that we can do as astronomers. But in order to do that in a convincing way, we also need to become active ourselves. So let me first give you the broad overview of what is the climate, and does the sun have anything to do with it? Don't worry, I'm not a climate denier. And then what is the current climate crisis? So to get these orders of magnitude right, let's say. So the sun, planetary orbits, and the climate. Of course, since you're all astronomers, we all know about the 11 or actually 22-year cycle of the sun. Every 22 years, the magnetic field changes, has one complete cycle, and every 11 years, you see an activity increase. And that can be seen on Earth. Already Galileo Galilei saw it, that there are more sunspots when the sun is more active. The space weather gets more extreme. Satellites start to have problems communicating. So this is a real impact on the Earth. Does it also have an impact on the Earth's temperature? Well, if you look at this graph until the 1960s or so, you could think, oh my God, there was a real correlation. And there were actually a number of people who claimed such a correlation and who said, oh, it's all the sun, don't worry, we have nothing to do with it. But as you can also very clearly see from this graph, if you continue this until a more recent time, there is a clear disconnect between these two curves. So the sun does its thing, so to say. You see the 11-year cycle imprinted over some variations that happen because the sun is, as you know, of course, an evolving star. And on the other hand, you see the actual temperature increase, which with a little bit of variation as well. There's a 0.2 degree or so annual scatter due to natural variability, like the El Niño phenomenon and other things that happen sometimes, instabilities in the climate system. But otherwise, there is this real, really very intense and very significant trend upwards that is clearly not connected to what is happening on the sun. So that is one astronomical impact, so to say, that we can clearly say, okay, it has nothing to do with the current climate crisis. And the other thing that is often mentioned by, let's say, by climate deniers or people who don't really want to tackle the human influence here is the ice ages. And they say, yeah, you know, the Earth's climate has changed all the time. And indeed, it was actually much warmer in the very, millions of years ago. And also the CO2 levels have already reached more than 400 ppm like we have at the moment. But if you look at the more recent past, like here, which is reconstructed from ice cores, they look at the oxygen 18 isotope, which is of course a bit heavier than normal oxygen. And so it gives you an indication of how much of the water was in ice, because preferentially goes into the ice, this oxygen 18 isotope. And from that, you can reconstruct the temperature record over the past several 100,000 years. And we see these variations happening about once every 100,000 years. So these are the ice ages that we had over the last roughly 1 million years or so. There are also other cycles imprinted on top of this. The perfect reason for all of this is not fully clear, but I'll come to the Milankovitch cycles in a minute. But you can also see that about 20,000 years ago, we had the last minimum. So that was the last minimum of temperature, the last big glaciation. And since then, temperatures have increased again, but over 20,000 years, so a long time, and have reached a pretty stable level over the last several thousand years, actually. So the reason for this, for these ice ages, is probably variations in the Earth's orbit. This was already studied by a Serbian well, astronomer, geologist. I'm not sure if these distinctions were there at the time, Milutin Milankovic, about 100 years ago. And he looked at at the connection between these variations. And more recent evidence shows that actually the most likely change that causes this 100,000 year cycle is probably the variation in inclination of the Earth orbit. And the theory that I read in this proceedings paper here that is quoted is that when the Earth orbit is more inclined against the ecliptic, so the orbits of the other planets, then you don't cross too much dust and dirt of the rest of the solar system, but when it is more or less inside the ecliptic, then lots of dust, cometary dust, for example, impinges on the Earth's atmosphere, and that might have a similar effect as volcano eruptions. So insolation, the radiation that is received by the sun, suddenly decreases, and that could lead to such an ice age cycle. That's the current explanation for this. Certainly, there is this similarity between the 100,000 year ice age cycles and the frequency of inclination variation of the Earth orbit. But okay, so this is something that's happening on very, very long timescales. We're talking about 100,000 of years. We can look at the CO2 concentrations. They follow the temperature changes in the past. And you can see these changes here that happen roughly once every 100,000 years. There's also a 40,000 year cycle imprinted on top of it, which is, I think, due to changes in the ellipticity of the orbit. But then you see at time zero, so roughly now, you see this sudden increase of CO2. And that is, although you can hardly see it from this graph, that is much steeper than anything that has been seen over hundreds of thousands of years. And that is, of course, our own impact. And the star is where the last trustworthy average number is. You can see it at CO2.earth. You can see the latest measurements taken from a worldwide network. And we're now at 416.5 parts per million, whereas we used to be below 300 for most of the time that humans were on this planet. And this number is really reaching very significant and very dangerous values. Another graph, I'm saying this not just to, I presume you know many of these things anyway, but I think these are some of the resources that I find most convincing. Also, if you want to use some of this to talk to other people, I'm happy to share my slides. This is a very, very nice graph that is made by Randall Munro, the maker of XKCD, a nice comic strip. He's a physicist himself. And he shows this really, really long comic strip that I abbreviated here because it's really, really long, that goes from 20,000 years ago. It's not always serious, so there are some jokes embedded as well. And you can see this very, very slow increase in temperature that started as about -4 degrees. So that was the minimum reached at the last ice age. And then it increases slowly until it reaches more or less the pre-industrial zero. That is now around since many thousands of years, actually. And then in the last about 100 years or so, it started to increase this rapidly. So that is this rapid increase. The rapidness of the increase is really what makes this climate crisis that we see now stand out. And again, another plot. This one, I forgot to add the reference here. This is from the US climate change program that separates natural drivers, that includes the sun, that includes volcano activity, that includes natural variations, and a couple of other things that are known. And you can see this, well, it has some variation, but if you include the human drivers, you can very clearly see that, especially after the 1960s, when burning of coal and oil was increasing very rapidly, you can see this very steep increase that can only be explained by humans. All right, and then to show the urgency of the problem, I think the best visualization for this is actually the carbon bucket. So there is a carbon budget that one can think of how much CO2 can be put into the air for the Earth to warm up by 1.5 degrees and not anymore. And the 1.5 degrees, as you know, is the goal agreed upon in the Paris Agreement. And at this level, it's relatively certain that no major disasters will happen. So, for example, the glacier, the poles will not completely melt. Forests will not completely start burning and go away. And a couple of other so-called tipping points will not be reached relatively certainly at 1.5 degrees. So this is really the level that we want to achieve. There's also talk about the 2-degree goal. There's just that still has the probability of a relatively low probability of major events, major disasters to happen, but it's not quite as certain anymore. And since it's such a sincere and serious effect, we probably want to be certain. So in this carbon bucket, you can see what are the emissions from various sources. And it's quite interesting to see, for example, that China so far has actually produced less to this bucket than, for example, the EU, and so considerably less than the USA. So that's important to know when you have these discussions of, oh, it's all the Chinese problem now, or it's all a problem of India. Yes, they are at the moment, China especially is the largest polluter at the moment, but from their perspective, of course, they see, oh, but you already have made all these emissions and therefore built up your societies in the way that you have it. So it's important to know this. There's actually also a nice animation behind this. Let me see if that works. Seems to. So you can see how the carbon bucket is filling up, and you can see how slowly this was in the beginning and mostly dominated by the EU and US, and then the rest of the world comes in, and then from the 1990s, 2000s, really China is rising up. And there is now this really, really tiny bit of just 9% or 10 years in 2019 left to stop the bucket from overflowing, so to say. If you prefer this in a graphical, in a usual plot form, this is how it looks like. And the 600 gigaton and 800 gigaton budget roughly correspond to the 1.5 and 2 degree goals. And you can see, of course, that the later we start decarbonizing, the more intensively and the more rapidly we need to decarbonize. And that, of course, is a big problem. Now you may say, oh, but I mean, the Corona crisis changed everything. Well, there's also research about this. In the first half year of 2020, when many countries were in lockdown, the reduction of the emissions was about 9%, as estimated by this group from, this is from the Potsdam Institute for Klimafolgenforschung. And so 9% is significant. This is actually roughly the decrease that we need per year from now on. Right? So we need every year that reduction. So we need to have essentially all the Corona measures in place and then add another 9% on top of it. Of course, that's unrealistic. We all want to go back to a more or less normal life at some point. But that just gives you an impression of how severe these changes need to be. Yeah, and I would also like to point out that these conversions between CO2 concentrations or carbon budgets and temperature increase, and then the temperature increase to climate tipping points, of course, they include a lot of uncertainties. For example, the exact role of clouds is still very difficult, apparently, to model in these climate models. And so there are some uncertainties in these models. And we should not assume that all these uncertainties will, of course, be, let's say, work out in our favor. We want to be really safe, right? This is the only planet that we have, so we need to rather decarbonize a bit too early and a bit too fast than say, oh, let's wait a bit more. Okay, on a bit more optimistic side here, there is this webpage, the climateactiontracker.org, and they compare both what is the current policy. You can see this in the dark blue or the intense blue strip, and you can see the uncertainty added to this, both uncertainty from the models and also uncertainty from the policies. And you can see that the current trajectory, if we just leave all the current regulations in place, including the Kohleausstiegsgesetz in Germany, that would give us 2.9 degrees of warming. That is significantly too much. And this is by the end of this century. This is the timeline here. But there are some pledges that will be renewed later this year at the Glasgow Climate Conference, and there are some more optimistic targets that would bring us almost to this 2-degree goal at least. We would really still like to have the 1.5 degree goal, which may be unrealistic, but at least we should push for it. But the 2.1 degree goal or the 2 degree goal doesn't seem to be so far away. And I think that's very important to know, because it's really not impossible to do that. We just need to get our act together. All right. But then, of course, the big question is, why don't we act? I mean, the science is clear. It has been clear since a decade or two at least. There was no question anymore among climate scientists that there is this big problem, and that we are causing it. So that's clear. I like to compare it to, if you look at your weather app and you see there's a 50% chance of rain, you probably take an umbrella. But if we see a 99.9% chance, it's really at the 5 sigma level and more, so more than 99.9% actually. Why don't we then act to save our only planet? And the reason for that, unfortunately, is really essentially lobbying by the fossil fuel industry. And if you like to read up about this, I mean, this is not a how do you say this, conspiracy theory or something. This is really very well documented by scientific evidence and written out by rather well-known people. I have these 3 recommendations for you. The latest one is from Michael Mann, who is one of the most distinguished climate scientists in the world, who has just published a book, The New Climate War, outlining what forces in society make us not act enough, let's say. And there's also a really good book by 2 German journalists about the German perspective of this. It's also a book in German only, as far as I know, the Klimaschutzlobby. And that talks in particular about what is happening in Germany, for example, about the Erneuerbare Energiengesetz, so the law for expanding renewable energy, and why is that not happening faster? Why are there all these weird regulations about wind power? Why is it so difficult for private people to start investing in solar energy? This wouldn't have to be that way, but it's really due to lots of lobby interests. All right, with this rather lengthy introduction about the climate crisis, I hope you're still with me. Let's get to the core of this talk. What can astronomers do? And I like to split this up into 2 big parts. One part, as I said in the beginning, is we can reduce our own carbon emissions. And usually there's often this pushback saying, oh, but astronomers, there's only, I don't know, 20,000 astronomers in the world. So what impact would we have? I mean, is it really worth it? I mean, are we not contributing so much to society by taking these beautiful pictures like the Hubble Ultra Deep Field? Should we not have an exception here and just go on? I think it's important to very clearly say no. We need to lead by example. We are scientists. We know, we trust the science that our colleagues, the climate scientists, put out. We know that it's a true warning. And if we don't accept this warning, and if we don't act according to this warning, then how can we expect others to see the urgency? So I think it's very important that we show that we're serious about this, and that we therefore really do whatever we can to reduce emissions. And then the second part, and I think that's even more important, but it requires point 1 to be taken, otherwise it doesn't work as well, is we need to convey our own perspective on the world. We need to get out this message of there is no planet B. I mean, this is really a core astronomical statement. There is no planet B, and what it means we can discuss in a minute. And that can have a very strong impact. There's lots of initiatives funded by the IAU and also by other bodies of this global citizenship idea that there's many aspects to reach this, of course, by connecting to nature and various other things, but astronomy can have a very big role in this. And that's certainly an aspect that we should emphasize in our public outreach. So let's start with the first point, our own carbon footprint. As a friend of mine said, telescopes run on diesel. That's unfortunately not quite true for all telescopes anymore, but still, astronomy is a pretty dirty business, and it's due to a number of factors. Fortunately, there is now several institutes have published climate or carbon footprint breakdowns. One of the first ones to do this was the Max Planck Institute in Heidelberg, actually, where I happened to do my PhD, but I'm not connected to this research. This was done by Knut Janke and colleagues, and they collected all the travel applications, let's say, of course, anonymized over a year, done for all travel at this institute, which of course was quite a lot. And also had surveys to find self-booked travel, well, to find the self-booked travel, and they computed what the travel emissions are from this. And this is, there's also some caveats to convert a flight to CO2 emissions, because it says here CO2 equivalent. What that means is that if I emit a ton, or hopefully just a kilogram or a gram of CO2, by burning it on the ground, that has a different impact than if I emit the same amount of CO2 through an airplane at high altitude, for two reasons. One is at high altitude, it has a different impact to the atmosphere, and also it's not just CO2 that is emitted, there's also water, for example, the contrails, and I was about to say chemtrails, but that's a different story. Contrails, and they have an additional effect on the climate. So all this combined makes the emissions of airplanes a factor of 2 to 3 more impactful than the same CO2 emissions on the ground. That's why people talk about the CO2 equivalent. So in CO2 equivalent, you have these numbers here, almost about 900 tons of CO2 from travel, another one from self-booked, and then you have electricity on-site, meaning running computers at the institute on the Königstuhl. Off-site is mostly supercomputing centers. Then there's heating, quite a bit, because on Königstuhl it's usually cold. And then there's commuting, a 5% factor. That's probably more than in other institutes, because it's of course located a bit outside of Heidelberg, as you know. And then a few other things that actually don't have a big impact, like meat served at the canteen. They took quite conservative assumptions here, does not have such a big impact here. They also say a few other things that they did not take into account, like train trips. But this, I think, is fine. You can assume that a train trip is usually at least a factor of 10, and probably much more lower in emissions than a plane trip. So these numbers can be put together and correspond to something like 9 tons of CO2 equivalent work-related emissions per employee. You can also break this down per paper if you want, and you can compare it to people in other places of the world, and you find that this is quite significant. A second study is being done. It's unfortunately not yet published, but I may show these preliminary results that the project leader sent me, Robin Arsenault, at ESO, the European Southern Observatory, which of course runs the biggest observatories for European astronomers in Chile. And they did a very careful, I mean, not that Knut's one wasn't careful, but they did a much more detailed investigation and actually hired a company to do that for them, Carbone 4, a French company run by climate scientists. And they took into account the different scopes for these emissions. So that includes what the institute or the observatory actually emits. So really CO2 emissions coming out of Garching, let's say, but then also upstream activities that include, if you buy a computer, CO2 emissions will occur somewhere else. So that's an upstream emission. And downstream, if you sell a computer, then someone else needs to use electricity to run it. That, of course, is less relevant for ESO because it doesn't sell computers. But upstream and the company activities itself, of course, are quite important. And if you take this all into account, this is the grand sum for ESO, 28 kiloton of CO2 emissions, equivalent CO2 emissions in the year 2018. So 2 years before Corona, of course. And this can be split up into various parts. And you can see already, compared to the MPIA the MPIA footprint, where travel was a big part, at ESO, the biggest parts are energy and purchases. Of course, that is because ESO's task is mostly to run observatories and not so much to do research or to travel around, but that also is a smaller part. If you look at energy in more detail, you can see that more than half of it is used up on Paranal. I should say that ALMA is not included in this analysis because it's not just an ESO facility. That would probably, well, I guess it would probably almost double the emissions here, but this is just for ESO's core optical infrared observatories. So at Paranal, a lot of the emission is being produced. It's currently running on natural gas facilities. And it's not quite clear to me why solar panels haven't been installed 10 years ago, because actually most of this energy is used during daytime when the telescopes need to be cooled to have the same temperature as they will have in the night to not have any dome seeing. So it's not that you need, I mean, of course you would still need big batteries to also store it at night, but it's really a lot of this energy is used during daytime, and it's usually sunny there. Well, that's the reason why we are there. The same for Garching. It's also a relatively sunny place, so also that could certainly be to a large part be covered by solar panels. Purchases, you see it's roughly 50-50 between IT equipment and other equipment. So that's of course building instruments, buying your piezo motors and optical benches and stuff, and a few other things. And for travel, it's mostly long-haul travel as expected, because of course flights from Germany to Chile, 14 hours is a significant part. This is similar to another study that has been done by Nicolas Flachéry for the Canada-France Hawaii telescope on Mauna Kea, where they find a 63%, that 63% comes from electricity at the summit and 25% from travel. The changes or the differences between these assumptions or these calculations is usually because the energy, the electricity, is coming from different sources. So ESO uses natural gas, which is relatively clean fossil fuel, whereas CFHT uses whatever mix they have on Hawaii, which presumably includes some coal or dirtier sources, or perhaps oil, I don't know. Apart from running observatories, building observatories was also a big thing for ESO. Building the ELT roughly amounts to 3 to 4 years of running everything at ESO. So that's a big part. But this is all not published yet, so I won't go into details here. But another project did recently publish their carbon footprint study. That's the GRAND project, which is a planned neutrino telescope with lots and lots of antennas distributed all around the world in radio silent zones. And they did a careful analysis, including the various parts that make up their antennas, including how much steel is required, and the solar panels that are used to power these antennas, of course, also need to be produced. All the digital technology, which is a lot for them because they produce terabytes and terabytes of data that will then be sent around the world to various data centers and be reduced and then stored in cloud storage. So that is a significant part here. And if you look this all up, it adds up to quite frightening numbers in the end. The GRAND 200K, their maximum level of running, you get something like 13,000 tons CO2 per year. So 13 point something kilotons. Let's just go back to ESO again. We're here at 28 kilotons for all of ESO. So this GRAND observatory alone is, well, something like half of ESO, which I think is quite significant. Okay, but hopefully by 2030, we have ways to make things a bit cleaner, especially in the digital part. Of course, we can use cleaner energy to run, to produce, to transmit data. And then the last part I would like to highlight is the publication that Volker already mentioned, the analysis that I did with some colleagues for the European Astronomical Society meeting in 2019 and 2020. In 2019, this meeting was physically in Lyon. It was a very nice meeting, but it was extremely hot there. And that was actually one of the reasons why a couple of us started to discussing about are we astronomers actually part of the solution or part of the problem? And in 2020, then, of course, things were fully digital. But let's first look at 2019. So we ran a survey and asked people where they came from and how they arrived in Lyon. And you can see here a histogram of the number of trips as a function of emissions of trip. And if you can see my mouse, you can see that there's, of course, a number of emissions from people in Lyon or nearby who either arrived, well, who just didn't have a long trip to go there. And then there is a huge peak at a distance of a few hundred kilometers. So this is the core of Europe, let's say Amsterdam, Berlin, Rome. All of these people can travel to Lyon within just a few hundred kilometers. But of course, or unfortunately, most of them still used the plane. 2/3 of everyone used the plane, also for trips that were less than just a few hours by train. And then you reach roughly 50% of all the trips. So we have 80 something trips. So here's roughly 50% is at the distance of Moscow. And you can see that there is not many trips made afterwards, so to say. Like I think it was 80% of all the trips, of all the people, sorry, reached here. But the emissions, the contribution to emissions is still pretty significant for these remaining 20% of people, because they traveled from far away. Like just a few people traveling from Sydney is of course more than many people traveling from Amsterdam. And then you can also ask who is actually traveling and who is traveling how much. This was analyzed by a colleague of mine through Astronomers for Planet Earth, so to say, by Adam Stevens at the International Center for Radio Astronomy at the University of West Australia. So they compiled the whole emissions of their institute, and they also looked at travel and who travels how much. And you can see here the CO2 emissions from flights for the different populations of scientists. And if you look closely, you can see that PhD students and master students are at the relatively low edge here of less than 2 tons of CO2 equivalent emissions. Postdocs are slightly more. There's also a lot of variation, but then senior scientists are really the ones who contribute a lot, who travel a lot internationally, and actually contribute something like 15 times more than PhD students. So again, important to keep in mind when people say, oh, we should travel less, you sometimes hear the pushback, oh, but the junior people need to build their network. Yes, that is true, but they're actually not the ones who are traveling that much. So it's most important for senior folks who already have the networks to reduce their travel significantly. Now in 2020, just to make this comparison, we had the EAS meeting, of course, virtually. This was a big success, I would say, the meeting in itself. We had almost 50% more participants than the year before. And we ran also an exit survey, found that 80% of people were online 5.5 hours per day. And then we did an emissions estimate for the laptops and for the network and for the Zoom servers. You can read this up in the publication if you like. And the important number here is that adding everything up, all the emissions for 1,777 people, so we scaled up the emissions, the answers that we got from the survey to everyone, assuming that we had a representative population. Then this means the emissions from all the people at this EAS meeting for 1 week of Zooming was roughly 600 kilograms. And this is roughly the same as a single return flight, so one flight back and forth between Liverpool and Lyon. Not very much compared to the year before, where 2/3 of all participants used the airplane. And you can also give the other number that the difference or the factor in emissions between 2019 and 2020 was actually a factor of 3,000. So 2019, although it was 50% fewer people, had 3,000 times more emissions than the online meeting. Or in other words, you can essentially completely ignore the emissions from online meetings and just try to make them as good as possible so that people will actually like them and use them. Okay, now that brings me to the second part. So we can reduce our own emissions, I think, relatively easily in several parts. We can install green energy and push for green energy at the observatory sites and also at our institutes. If you have a flat roof, just get a company to install solar panels, if that's possible, by your university. You know, there are companies now around that do this for free, and then they sell you their electricity for a lower price than you currently pay. So it's really a win-win situation for everyone. You just need to convince your university to do it, which is not easy. I tried it in my university and failed, but nevertheless, it is possible. MPIA, for example, is doing it right now. But okay, this brings us to the second part. So we can reduce our own emissions, and then what else can we do? Some of you may have participated in climate demonstrations, and then you see the sign, often there is no planet B. What does that mean? Well, of course, we're searching for planet B. The project for which I mostly work, METIS, the big ELT instrument, has as its prime goal to find a planet that is like the Earth in terms of size and atmosphere and temperature and so on. So that would perhaps be called a planet B. But of course, what is meant with planet B is there another planet where we could live? And every one of us, or most of us, could go there? And the answer to that is clearly no. Also, if Elon Musk manages to civilize or to produce an atmosphere on Mars, this will still be so expensive and so difficult that it will not be a solution for our own climate problems. Right? We will not be able to replace the Earth by anything else. So we really just have this one planet. I mean, this is probably clear to everyone, but I think it's important with all the science fiction sometimes around to make this clear that, okay, we know thousands of exoplanets, but none of them is like Earth, and even if we couldn't go there. So that's, I think, one part that we can share with the population, with the wider public, that it's fascinating to look at all of these exoplanets, but it's not an alternative for saving our own planet for us. The other big thing that we can do is to communicate facts and methods, like, for example, this nice graph here from NASA showing what the sun activity, what the sun's activity was over the last decades. We can explain what the solar dynamo is and how the solar cycle works, and how it has no relation whatsoever with the temperature increase that we see, to just really split these things up. And we can also explain some of the methods. Like, I mean, it's not difficult to read a paper by climate scientists that, you know, they're written in a scientific language that you and I can understand. And they explain, for example, how this oxygen 18 method works. And then it's, you know, once you explain this to people, to see, okay, this is not black magic that comes out of nowhere, but it's actually very simple to understand. It's just a heavier atom, and it's more likely to drop into the water and to drop into ice rather than be in the air. And if that increases, you have an increase in ice fraction. And apart from just explaining things, there's this other aspect that astronomers are typically trusted by the public, because we do cool stuff, and we do things that are politically not controversial. And so we can communicate about climate science if we want, or tell about climate science. Of course, we're not climate scientists ourselves, but we can tell about their results from the neutral ground. So we can say, look, this is what they say. We have read their articles, and this is how it works, and not be directly in this in this line of, oh, you might be politically, you know, bought or something else. And I'm nearing the end now. 2 more slides. Thank you for staying with me. But this is, I think, perhaps even the most important part now at the end, the perspective that we can share. This was my title slide as well. You might have you certainly have seen this slide before. This very iconic image is called Earthrise, was taken by Apollo 8 astronauts as they circled around the moon, and they saw for the first time the Earth rise behind the moon, and they had this completely different perspective on Earth, so to say, to see it really as this marvel in space surrounded by nothingness. It's of course even stronger on this other very iconic image, the pale blue dot, that was taken by the Voyager 1 space probe after it has passed most of the planets that it visited. So roughly behind Neptune's orbit, it turned back towards the sun, which was a very difficult operation actually, because the antenna to communicate with Earth was on the other side. So telling it to turn to the back to take an image of the sun and the Earth meant that the communication antenna was looking outside into outer space. And so they had to be pretty sure that their program to turn it back afterwards works again, but fortunately it did, and it was still active afterwards. And of course, there is this very, very tiny point here that's 0.2 pixels wide on this image. That is the Earth. And that has a very profound effect if you take it to your relatives and friends and just show them this image at some point to really show, wow, this is space, right? It's huge. I mean, we all know this. We were used to working in megaparsecs and logarithms, but show this image once and you will see a very, very profound reaction, even by sophisticated people who know lots of things in other branches. But when they see this image, to see this is lots of nothingness, and then us, this has a very strong effect. So with all of this, I would like to finish. Thank you for your attention. I have a couple of resources here on my last slide. And of course, would like to highlight the organization Astronomers for Planet Earth, which has now about 800 people signed up. It's essentially a network. We have a Slack space and a mailing list where we just share information and find people to work together with on various aspects. We have published a range of articles already about this topic, and you're very much welcome to join us. Just go to the webpage, sign up. Then what you will get is a link to join Slack and our mailing list. And then you can read a bit, and you can also leave again, or you can start discussing or become active as you wish. Okay, so that brings me to the end of my 45 minutes. I would like to thank you again for all your attention, and looking forward to a good discussion. Thank you.